I first like to congratulate the Korea Foundation for Advanced Studies for this occasion of 40th anniversary. I'm very much honored to give a talk in this occasion and thank the organizers of this symposium for the invitation. And unfortunately, mathematicians especially are well known for blackboard talks. And to be honest, in my whole career, if I remember correctly, this talk would be the 5th or 6th electronic talk. So please allow me to be very clumsy in giving this electronic talk. So in this talk, I would like to describe what I've been doing for the last 20 years, but mostly the description of the area, only in the last maybe slide, I would like to say one word about what I'm doing. The origin of this area, I would say, come from classical mechanics, and one particular relevance in quantum mechanics is this uncertainty principles. And as most of you know, Heisenberg uncertainty principle is one of the basic principles in quantum mechanics, and it can be written as delta pi times delta qi is not less than this Planck constant h. And here qi and pi are so-called conjugate coordinate, momentum and position coordinate. And this equation can be interpreted as the measurement of the position and momentum cannot be made precise at the same time. Furthermore, the possible minimum of the product of errors cannot be smaller than Planck constant. In the more simplistic terms, what it means, the more precisely we measure the momentum of a tiny particle, the less precise becomes the measurement of its conjugate position coordinate. And what I would like to emphasize in this inequalities is the area of projection to each coordinate plane. So if you imagine a tiny particle in space, you look at the location and its momentum simultaneously, and you project this information to any of these coordinate plane of conjugate coordinate. And the geometric structure of measuring such a quantity is called the symplectic form in mathematics. This is basically the sum of the area of the projection of domain in so-called phase space. And the general curved space allowing such a symplectic form is called the symplectic manifold. And symplectic geometry is the study of the geometry of such an object. And the most basic example of symplectic manifold is nothing but our phase space, the classical phase space. And in classical Hamiltonian mechanics, the motion of conservative system is described by so-called Hamilton's equations. And the physicists define the notion of canonical transformations as the kind of transformations which preserves this form of ordinary differential equation under the change of coordinate. And one of the fundamental properties of such a flow is that it preserves the volume of this phase space. And the mathematical definition of this canonical transformation can be stated as the transformation preserving this symplectic area or symplectic form. And then the Liouville's lemma is nothing but the corollary of these definitions, which says the transformation preserves the cube of this omega. And pictorially, what Liouville's lemma tells you is the following. Suppose you're given a ball of certain volume, and you let this domain move under the Hamiltonian flow. And of course, the domain will change the shape. However, the phase volume of this shape will not change. So in this regard, it is very hard to see the difference between this Hamiltonian flow and some volume preserving flow in phase space. Even though definition is very different, however, empirically it's very hard to detect the difference between Hamiltonian flow and this volume preserving flow. And it turns out this question is very much related to these Heisenberg uncertainty principles. And understanding this one can be regarded as some kind of classical remnant or analog of this Heisenberg principle. And in 1960s, two Russian mathematicians, Arnold and Gromov, formulated the following questions. The question is, does there exist a canonical transformation squeezing a ball of radius capital R into the thin cylinder over very tiny disk of radius R? And if this question is answered affirmatively, this will manifest an empirical difference between this canonical transformation or Hamiltonian flow and the volume preserving flow. And these two are the mathematicians, one is Arnold and Gromov, who studied this whole question. And these questions withstood its solution for last 30 years since the question was formulated until 1985, or more precisely 1983, the preprint came out, and Gromov proved that such a such a squeezing is impossible when the radius of this ball is greater than the radius of this tiny disk. And here it is important, this disk lies in the coordinate plane of Q1 and P1, the conjugate coordinate. If you change this P1 by Q2 or Q3, such a squeezing obviously always possible. But here is this interplay between this momentum and this positions conjugate entering in this question, solution. Obviously, if the radius capital R is smaller than the radius of this lowercase r, it is obvious to put this into the cylinder by translation. And to understand how the Gromov came about, this solution is, I needed to explain three geometric structures on our classical phase space. I guess the first one is Euclidean inner product. We all learned in, I guess, in college. And then symplectic inner product. This is the kind of product which measures the area of the projections on this plane of conjugate coordinate. And then if you regard the six-dimensional real vector space as the three-dimensional complex vector space with that change of coordinate, and there is operation of multiplying square root of -1. This is called complex multiplication. And each of these structures carries the symmetry group, which preserves such a structures. The first one is so-called orthogonal group. The second one is called the symplectic group. And third one is called the general linear group of complex numbers. An amusing fact is that the intersection of any pair of these three groups turned out to be the same, which is nothing but the symmetry group of so-called Hermitian inner product. And if you globalize these geometric structures, you will get the so-called manifold in general. And the Riemannian manifold is the manifold with this Riemannian metric derived from this Euclidean inner product. And symplectic manifold is the manifold with equipped with this symplectic form. And complex manifold is the manifold equipped with this complex multiplication on its so-called tangent space. And one of the very important observations of Gromov is that any symplectic manifold, there is some kind of complex multiplication on each tangent space. And such a structure is called almost complex structure. And this structure is not unique, but there are plenty of them. And one particular class of almost complex structure is called comparable to symplectic form. When this compose the symplectic form together with the complex multiplications becomes positive definite. In general, this composition may not be positive definite. Okay. And then the revolutionary idea of Gromov was that you study some maps from the compact surface. Sigma here is some kind of two-dimensional surface. Imagine the donut with many, many holes in general. Maybe this surface may have a boundary too. And then you can think of some particular map, so-called holomorphic map, that intertwines these two complex multiplications in the domain of the map and the target of the map. And you use this kind of object to prove this given ambient symplectic manifold. In mathematics, especially in topology, what mathematicians usually do to understand the structure or topology of ambient space, what they do, they send some probe of some object into the space and see how this object behaves under some kind of deformation. And what Gromov observed is that for the symplectic manifold, this probe is kind of the objects of pseudo-holomorphic curves should be the kind of probe to extract the information of underlying symplectic manifold. So in relation to these non-squeezing theorems, the ambient space will be these thin cylinders. And in mathematics, one of the most fundamental questions is that when you define some object or structures, and the question is whether such a definition is vacuous or not. So to see whether such a definition is good, you have to prove some kind of existence theorem of such an object. And it turns out this existence result of certain holomorphic curve through a given point in the thin cylinder would be the key to answer this non-squeezing result. And this existence question turned out to be greatly aided by the flexible choices of these comparable J's. So here is the picture. So what this picture represents is the following. Suppose you are given this squeezing canonical transformations, assume, and then you send the probe of this holomorphic disk into that thin cylinder and try to find such a holomorphic disk that pass through the image of the center of that ball there. And that's the most difficult question to answer in this whole proof. Prove the existence of certain holomorphic disk that pass through that given point, image point of the center of the ball. And once you prove such an existence, and then this will give rise to some contradiction when the radius of this ball is greater than the radius of this thin disk. That's the way how the proof goes. Okay. And so in mathematics, to understand this kind of existence question, very often they define certain invariant, which is kind of rigid or stable under certain deformations. And around the same time, this kind of invariant used by holomorphic disk was also defined by theoretical physicist Witten in his study of so-called nonlinear sigma model in string theories. And implicitly, Gromov used this kind of invariant in his proof. And because of this, now such an invariant is called Gromov-Witten invariant in mathematics, also in physics. And when the Riemann surface, sigma, or the compact surface I mentioned, has no boundary, they associated this Gromov-Witten invariant is some kind of outcome of so-called closed string theories. However, when the Riemann surface, sigma, has boundaries, and it is always very important to study both in physics and mathematics to find the correct natural boundary conditions for the equation of motion to behave nicely. And in fact, such study of such a natural boundary condition in string theory led to the so-called open string theory of de Bruyn's. And this is very simplistic picture of you look at this compact surface with the boundary, and then you send this surface as a probe into the space there with some brain floating around, and then you want to understand the whole totality of such an object. And in symplectic geometry, the natural boundary condition for pseudo-holomorphic curves involves so-called Lagrangian submanifolds. I'm sorry to be technical. However, you can imagine the set of particles with zero momentum in phase space. And the dimension of such space is exactly 1/2 of the ambient space. Or you look at the set of particles with fixed positions. These are typical example, very naive example of Lagrangian submanifold. What's important is the understanding the long-range interaction of these two Lagrangian submanifolds. And the long-range interaction of this Lagrangian submanifold are so-called described by flow homologies. This flow homology is the kind of things I have been working on for the last 20 years. So that's the only thing I can say about here. And the category formed by this set of Lagrangian submanifolds with that kind of long-range interaction is called Fukaya category. And this is some kind of spine of understanding the symplectic manifold. And similarly, in complex geometries, the corresponding boundary condition involves so-called complex vector bundle or coherent sheaves. And the category formed by this coherent sheaves are so-called derived category of coherent sheaves. And these two geometries completely look very different. However, in physics, there's some kind of very mysterious way of relating these two. They're called dualities. And in fact, in 1994, one of the field mathematician Kontsevich formulated the following very general conjecture or proposals. There is the very renowned space so-called Calabi-Yau manifold. And this Calabi-Yau manifold carries its mirror, I denote, and then the proposals conjectures the category of this so-called Fukaya category of symplectic manifold will be isomorphic. The category of derive the category of coherent shapes in complex geometries. So this is some of the special cases have been proven. However, the proof is not really a proof. Both sides explicitly and see the isomorphic. But one of the crucial problem is to understand why this duality happens. So this is some kind of mathematical question which has to be answered for next to maybe. Thank you for your attention.